I'm Jyotishman Das, and today I will be presenting the paper GOFA, a Generative One-For-All Modeling for Joint Graph Language Modeling as part of our major examination of Foundational Models and Generative AI. This paper was accepted at ICLR 2025. Uh, so this work introduces a foundation model style approach for graph data. So, as you all know, graph is an area where such models have traditionally struggled. So first, let me walk you through the outline what we will be covering today. Introduction, problem statement, obviously. Then we have the desired GFM properties, unified task representation, all the evaluation and results, the limitations of existing approaches, the GOFA framework and architecture, the pre-training task, and finally the conclusion and future work. So let's start. Rise of foundation models. So foundation models in text and vision have shown remarkable generalization due to large-scale self-supervised pre-training. However, graph data is fundamentally different and structures vary widely across domains, and existing models cannot unify graph understanding with generative abilities. So, in the paper, the authors have highlighted that no current graph foundation models simultaneously achieve large-scale pre-training, task fluidity, and deep structural reasoning. As you can see in the next slide, that's the problem statement. No existing graph foundation model jointly achieves these three. So GOFA aims to bridge this gap by unifying structural learning with generative language modeling. Yeah. So this is the current landscape and limitations. So there are two dominant approaches before GOFA. One is LLMS predictor, second is LLMS enhancer. So LLMS predictor is where graphs are flattened into text, as you can see in the diagram here. This supports flexible generation but lacks structural understanding. And second is LLMS enhancer, where LLMs improve node features for GNNs. Like this captures structure better but loses generative flexibility. And GOFA aims to combine the strengths of both. So these are the desirable properties of a GFM. So the authors define three key properties for a graph foundation models. One is the large-scale self-supervised pre-training. Second is fluidity across tasks using natural language instructions. And third is graph structural understanding, such as shortest paths and common neighbors. Like these properties drive the model design. Yeah, so this is the generative graph modeling framework. So the GOFA operates on text. Text stands for text attributed graphs, where every node and edge is represented using natural language descriptions. For any query, a designated node of generation or NOG is chosen, and the model generates text for that node conditioned on its graph neighborhood. Like as you can see the formula here, this formulation allows many graph tasks like classification, QA, structural predictions to be expressed as conditional text generation. So yeah, so this is the methodology overview. So like the pipeline has mainly three components. One is the ICAE compressor. It compresses each node's text into a small set of memory tokens. Then comes the GNN layer, interleaved token level GNN layers, like inserted inside a frozen LLM, allowing structural message passing. And then at last, then comes the LLM decoder. It generates free form outputs for the NOG. So the architecture enables the model to retain generative ability while gaining structural awareness, something neither pure LLMs nor pure GNNs offer. So this is the GOFA architecture, as you can see. Uh, like the GOFA integrates initialized GNN layers into a frozen pre-trained LLM. From the architecture, you can see the graph language encoder randomly initialize GNN layers into a frozen LLM, as I spoke earlier, which enables token level structural message passing while preserving the LLM's semantic knowledge. And that's the outcome. The model retains free form generation abilities while gaining structural awareness. Yeah. So these are the key model components. Hmm. Yeah. One is LLM Composer and token level GNN, which I have already talked about earlier. Like as you can see, since GNNs need fixed size inputs, we use an ICAE to compress node sentences into K memory tokens. And second is token level GNN. They extend standard GNNs to operate on the memory tokens. I will talk uh, about it later on when we move ahead. So yeah. Then comes the unified task representation. So all downstream tasks are reformulated as K-hop rooted subgraphs around target nodes. A special prompt node, as you can see in the architectural diagram, containing the user instruction is inserted and connected to relevant nodes. During message passing, the prompt node conditions the representation of the NOG on the task. This unified interface allows GOFA to handle classification, QA retrieval, and structural reasoning with the same model. This is the pre-training tasks. Like the authors designed four self-supervised tasks: sentence completion, structural understanding, QA chain reasoning, and information retrieval. So sentence completion is generating masked spans using both textual and structural context. Structural understanding is like generating shortest paths and predicting common neighbors. QA chain reasoning is like answering questions based on multi-turn conversational chains, and information retrieval is like retrieving node content given its ID or retrieving the ID given content. So together, all these four tasks teach the model semantics, structure, reasoning, and retrieval. So these are the same stuff which we have discussed earlier. The foundation and structure. In foundation and structure, we have sentence completion structure, structural understanding, and then comes the fluidity and retrieval, where questioning, question answering, QH, and information retrieval comes. Then comes the experimental setup. So like GoFi is pre-trained on several large graphs, MAC 28 PubMed, Wiki G90 MV2, the proposed Wikigraph, and UltraChat 200K for conversational reasoning. This mixture provides both structural diversity and rich textual descriptions. Yeah, so compared to its base LLM Mistral 7B, GOFA achieves lower perplexity on tech corpora, so demonstrating improved graph condition generation, as you can see from the table here. On structural tasks like shortest path distance and common neighbors, GOFA also shows clear improvements validating the benefit of interleaving GNN layers. So as you can see, it's mentioned here, improvement is significant. There's 50% reduction on shortest path distance and like 70% reduction on common neighbor, which is root mean square error. Now comes the zero shot results. So like after light instruction tuning, GoFi achieves SOTA zero shot accuracy on multiple graph benchmarks. It outperforms strong LLMs such as Llama 2 and Mistral, as well as graph specific models like OFI and Unigraph, as you can see from the table here. These results highlight GoFa's ability to generalize to unseen datasets and tasks. Uh, so now comes the scaling and ablation studies. So like performance increases consistently with more pre-training tokens, including that GOFA benefits from scaling. And ablation studies show that removing Wikipedia-style long-form text reduces performance on knowledge-intensive tasks, while removing the retrieval tasks harms multi-hop reasoning. This confirms that every component of the pre-training strategy contributes to the final model. There's the case study, which I talked about earlier. Like the case study demonstrates GOFA generates complete shortest path sequences and not just distances. Like it enumerates multiple valid paths, showing that the model has learned structural reasoning and can express it through natural language description. And yeah. So the conclusion, the limitations, the future work. So like to conclude, GOFA presents a unified approach for graph language modeling by combining text and ICAE compressor, token level GNN layers, and an LLM decoder. Like the model shows strong generalization, structural understanding, and flexible output generation. And the author's notes limitations like zero-shot evaluation is performed mostly on familiar task formats, and the frozen compressor may limit adaptability. So the future work includes better training strategies, broader task diversity, and exploring more challenging zero shots settings. So yeah, thank you for listening, and yeah. Thank you.